Here we are. This is the final lab of this weather and climate series of this course. So that is lab 11, uh, and today I'm going to make on a single video that includes a presentation as well as a lab tour. So just keep in mind. So this is a last assignment for you, the lab and the quiz. So after that, like I've already updated your six of the labs. So lab 1 through 6. So if you have any question about them, just ask me. If you have any confusion or questions, and other labs will be updated. Some of them will be updated by this week, and hopefully within few days you'll get the grade uh, updated from my side. So let's start this lab, which is lab technically lab 11, but you will see it as lab 10. Let me show you. So those who've already uh, attempted those lab 9 part 1 and lab 9 part 2, so those have been counted as your lab 9 and 10. So lab 11 today, this week is lab 11, and there is the presentation in lab 11. This is the presentation feature climate change PowerPoint. Let me download that first. So we will be talking about in this lab we will be talking about future climate change. So on lab 9 part 1 and lab 9 part 2, what you did actually, let me show you. Lab 9 part 1 you did, okay, climate literacy. Let me go to climate literacy. For lab 9 part 1 you actually studied about the recent climate things on two part, and now with all the speculation, all the study, all the information that you've gathered so far from lab now 1 to lab uh, or for 10 of the labs, where 2 is on lab 9 part 1 and part 2. So technically you've already finished 10 labs. So among those 10 labs you've studied like how temperature, how climate changes, what is the effect, what is going to happen. So you got some idea about that. Now lab 10 is actually talking about the thing that we should be concerned about. So what's going to happen in the future? So lots of the things that we've been hearing on news, on journals, on any other places, like we already know the sea level will rise, we already know that global temperature will increase, and blah blah blah, like some of those stuffs you already heard a lot about them. But this lab actually tried to help you understand how, why is that happening. So this lab, final lab, that will also talk about how is things going to happen, and like you will be an efficient person to know more about these things, and you'll know like these are some of the important things that you need to know as part of your own understanding, as well as part of conversation, a scientific conversation with other people. So right now at this point of time, if you have done all those labs properly and with these final lab, you'll be able to have a very very clear picture of what's happening around the world, and how should we prepare and what should we expect. So you are in a better position to talk about these things with your peers. So let's start. Without further ado, let's start our presentation. So here's the presentation file, lab. Okay, so lab 10 technically, which is your 11th lab. So I believe you already don't have any confusion about that now at this point. So let's start the presentation first. So this lab will be talking about future climate change. These are the research question. Number one. Okay. So number one question is like the idea of this lab is on these research questions. So number one is that by the end of the century, how are temperatures across the globe projected to change under scenarios with increasing carbon dioxide concentration? So I've already learned that carbon dioxide concentration is increasing all around the world, and there is very less we can do to minimize the carbon dioxide concentration. If we continue to proceed the way we are doing right now, so there is very limited chance for us to limit the emission of carbon dioxide. So like if that is continued, then what's going to happen? If that is increased, what's going to happen? If we can minimize the carbon dioxide emission, what's going to happen? So there will be some scenarios as it's saying in here. I will talk about that in the lab tour. So there will be some in fact in this presentation as well, there will be some scenarios where you will be introduced with the situation that's going to happen by the end of the century. And then question two will be, how will continued increases in global temperature affect the global hydrologic cycle? So as well as the hydrologic cycle that includes the precipitation, the soil moisture, and as well as the sea level and lots of other things in the hydrology. What's going to happen if the temperature is going to increase, or what's going to happen if the temperature can be controlled by controlling the carbon dioxide emission? So these are the things you will also know about that, what's going to happen in the future. And finally, if global warming persists, which is still going on, and we expect that it will go on, it will increase, and global warming is going to happen more rapidly in the future. How will the distribution of biomes at the end of the century differ from the current distribution? So previous labs, probably on lab 9 part 1, you've studied what happened in Atlanta. That was probably some years, 21,000 years ago, I guess. So, what was the biome of Atlanta 21,000 years ago, and what is it now? So, you studied that, you know from that lab that biome changes, right? Biome shifts. So, it changes its position, it shifts from one place to place. So, what's going to happen with the biomes? Which biomes is going to get affected rapidly? So these are the things you will get to know from this lab. So this is really cool lab, as well as alarming for you, for us, for the humankind. So let's do the recap of all those things we've done so far. So as we always talk about, human activities have contributed to global environmental changes. So we already know the anthropogenic activities. There was some question about that, and most of you answered the coal burning, the fossil fuel, the vehicle emission, and those are all other types of things. So those are all related to human activities that we've studied so far. We always talked about this one. And then number two, emission of GHGs, that means greenhouse gases, have severely impacted atmospheric process and energy budget. So lots of greenhouse gases are there. So I will also show you a list of greenhouse gases that impacts the global energy balance. So you've already studied that, how the greenhouse gases actually change the energy balance, how it actually increase the temperature, how it helped to negatively to increase the global to process continued effect of global warming as well. So that's also studied about the greenhouse gases. Some of those things will be reviewed again in this lab as well. Then the final one, changes have been observed in the atmosphere, hydrosphere, cryosphere, and biosphere. Some of those changes you've studied already. How zinc changed, how carbon dioxide storage changed, carbon storage changed, and how temperature changed. Lots of different things, lots of different changes you've studied so far. So some of them, this lab is actually based on the future. So as what happened in the past, we can assume that what's going to happen in the future based on those things that happened in the past. So that's the recap. The next lab, I mean, next slide is actually have a video about the radiative forcing. I believe these types of these ideas. I'm not sure about this video, but these about radiative forcing. You've studied something about radiative forcing on lab 9 part 1. So I'm not going to play the video in here. Just download the presentation file and watch the video by itself. Then climate models. So I already talked about the scenario. representative scenario in the first slide, second slide actually. So what is the scenario? We'll talk in details about them in the lab, and most of those things are actually in the description. So in descriptions of the lab. So I'm sure at this point of lab you already know that whatever I'm talking about, it's all actually related to the lab content. It's from the lab itself, not nothing from my own experience, nothing from my own knowledge. So it's really easy for you if you just follow the instruction on the lab, climate literacy lab. So it's really easy. I'm just trying to have you just see how to proceed with that. I'm not adding anything extra from mine. So why I'm saying that, because by saying that I am just asserting the fact that this lab instruction on the climate literacy lab itself, as well as the presentation itself, are more than enough to answer these questions. So what is the representative concentration pathways? So there are scientists actually created four different models, uh, which they actually named as RCP, representative concentration pathway. So this is the historical data, like what is that for radiative forcing from greenhouse gases. So this has been the historical data from 1900 to 2010, 15, something like that. This happened so far in the black, and from here on, scientists have predicted four different pathways. What are they? So scientists have assumed that by the end of 2100, this is the 2100 bar, by the end of 2100 year, like this century, uh, if we follow this path, this will be the RCP 8.5. So this is the RCP you see from here. This is the RCP 8.5 in 2100, like end of the century. So this path will take us to 8.5 watt per square meter more, like 8.5 watt per square meter radiative forcing of greenhouse gases by the end of the century. So to achieve this, I mean, it's not a good thing definitely. If you are there, that means you actually have emitted lots of carbon dioxide, you have actually emitted lots of methane, you've done lots of deforestation, you messed it up actually. If you are in this route, and by the end of this century, if if this RCP value is actually 8.5, that means you actually didn't do a very good thing. You did it really worse. So this is one of the pathways, and then there's next one, which is RCP6, which assumes that if the radiative forcing has to be in 6, still that is greater, like that is worse than now. So now it is in 3. So if it has to be in 6, then still it's bad for us definitely, that we are going so far. Like there will be some different scenarios. Excuse me, give me a moment, I got a call. I'm just pausing the video for a moment. Okay, back again. So here we were, before I left for my phone call. So this is the RCP representative concentration pathway. So these are the three scenario: RCP 8.5, RCP 6, RCP 4.5, where we can expect that by the end of this century, the overall scenario, like in emission and everything, will increase. In these three scenario, only the RCP3, which you can see there's a P and D, which means peak and decline. So only this RCP3 would be the one that will peak at some point, probably in 2040, 2045, I guess. There will be peak. Okay. There will be peak by this time on the green line you can see, then it will decline. So this is the only scenario that will actually improve the situation by the end of 21 this century, by the end of this century. So this is the only scenario, and this is really 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 hard to achieve, because so far we are actually trending in the upward direction. No way near a good scenario. So you cannot expect that we will do really really good, and by the end of this 21st century we will turn things around. It's not really possible, especially lots of countries, as we have already seen about China, India, and few other countries. They are going through their industrialized session of their economy. So they are actually expanding really huge. So definitely they will play crucial role in these warming scenarios and everything. So you cannot really expect very good things to happen by the end of this century. So that's my opinion. It can change. Very drastic things can happen. Like the you already studied about the Clean Air Act. So one of the very few act that has had really 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 great impact on our situation of our climate. So something like that can happen in the future. If that happens, if everyone abides by that act and law, hopefully things can turn around. But I don't see much hope if things goes like this right now. So there's the description. You can find the description in here. Then the next one, RCP SRES, what are they? So there is another one here, RCP 8.5. How is the carbon dioxide, atmospheric carbon dioxide change if RCP 8.5 continues, if RCP 6 continues? So atmospheric carbon dioxide right now it's here at 400 ppm. You've already answered one of the question in previous labs where you say that carbon dioxide ppm is 418. You got that number from a website. So if RCP 8.5 continues, it will take the carbon dioxide concentration to all more than 900. So that's really really more than double. Then RCP6 will actually take it to almost 700. 4.5 will take it to 550, and the 3, that will actually have the declining effect, not much, still greater than now. So that is RCP3 PD, that will actually take it to almost around, keep it around 450. So one of the things, very important thing to remember, you've already answered one of the question about carbon dioxide. Even though we reduced the we tried to reduce the emission of carbon dioxide, and if even if we reduce the emission of carbon dioxide, the scenario of carbon dioxide that is there already won't change that much. Why is that? It's because of the lifetime of carbon dioxide. So the carbon dioxide we already emitted. So now if we stop carbon dioxide emission from today, you cannot say that tomorrow there will be no anthropogenic carbon dioxide, because the carbon dioxide that have already been emitted, they will continue to roam around for about 100 years. So that's their lifetime. So you cannot expect sudden improvement of carbon dioxide situation if you implement anything drastic. So that's particularly for the carbon dioxide. For other greenhouse gases, situation will depend mostly on their lifetime. So projected change. So this is the global projected mean global temperature increase under the 4 different emission scenarios. So right now this, let me see if I can zoom this picture or not. Okay, so you will get these things in the lab as well. So right now, if you continue to this current trend, by the end of this century, the temperature would actually increase to 1.5 to 1.5 degrees Celsius increase. So but if the scenario 8.5 continues, which is the really bad one, it will increase 4 degrees Celsius. For scenario 6, that will increase almost 2.5 degrees Celsius. For 4.5, it will increase about 2 degrees Celsius. And for 2.6, is about 3, whatever it is, that will actually have some stable impact. So these are the four scenarios, and here's some information. RCP 8.5, 6.5, and 4.5 overestimate the future scenarios if current carbon dioxide trends are to be maintained. So, based on the current trend, these are the three things that has the overestimate effect, that is actually showing the extra effect about carbon dioxide situation. And then the RCP 4.5 is a middle ground scenario. Its extrapolation matches current trend in temperature. Just keep those things in mind. Like RCP 4.5 is actually close to the current trend. So, likely chance that we are actually continuing through RCP 4.5 scenario right now. So, sea ice cover projection for northern hemisphere. What's gonna happen in terms of sea ice? As you can see from this graph, the general trend is it will definitely decrease. So, sea ice expected to decrease in the thickness and extent. So, the thickness of these sea ice layer will decrease, as well as the amount, the area of sea ice will definitely decrease. And then Arctic is projected to be completely ice free under RCP 8.5. If RCP 8.5 continues, then definitely by the end of the century, we will see some summer when there's no ice on Arctic. So, just also it's important to know that RCP 8.5 is uh, not what we are at right now, based on our own consciousness and scientific theory on everything. RCP 8.5 is really difficult to obtain. Like, human will not do that harm to the environment, or the current trend of civilization, industrialization won't actually need RCP 8.5. So RCP 8.5 is a far-fetched scenario. This is just a scenario, so it's not practical, it's not real. Same as RCP3, which is also not possible to maintain. RCP 8.5, which is really difficult for us human to work like that, but we will be around RCP6 or 4.5, like that. So if it was in RCP 8.5, we would see the ice free situation in Arctic, but I believe things will turn around, or if things goes in this current trend, still we'll see some ice in Arctic. So then the one, and this is the really crucial information: climate types are expected to shift northwards. I'll show you a file where you'll see that climate, they are actually shifting towards north. So just to give you an example, so few hundred thousand years ago, we have seen the whole of Canada, and also the top part, like uh, what do you say, the northern part of the United States were covered under ice. And then as time went on, like, we saw that the ice cover is actually shifting towards the Arctic. So most of the ice is now concentrated towards the Arctic. Most of the ice is actually are removed from USA, the part of the Canada. So this is an example that climate is changing. This is an example that something is shifting. So this ice is actually shifting, or the temperature from the bottom is actually going up. So that's, I will show you that in my presentation, in the lab tour. So just keep that in mind. Climates are actually shifting northwards, and it's actually specifically decreasing the tundra. So I'll show you what the tundra region is about. So that is ET tundra. So it is actually decreasing, so we will see that. And just keep these two information in mind. I'm just giving you a heads up. So if you know this perfectly, if you just keep that in mind, you will get two easy marks in some two of your question. So this is the end of the presentation. I'm gonna straightforward go to the lab tour. So let's go to the lab 10, feature climate change. Okay, so here as usual, uh, watch the video from Mila for the last time, and you will get some ideas about this lab, and then go to section 1. This is the one you already studied in your lab 9. So this is what happened: changes to the climate system associated with the energy imbalance. You studied about that energy balance in some one of your lab. So this is the description as usual. So from section 2, where we should start, the section 2 is about radiative forcing agents in climate models. So this is the radiative forcing agents. Let me zoom in here. So these are the things. There's lots of forcing agents. Some of them are greenhouse gases, some are aerosols, and others. So among the greenhouse gases, you can see carbon dioxide, methane, nitrogen dioxide, tropospheric ozone, stratospheric ozone, CFC. And from aerosols, you can see these are those aerosols. You've already studied some of those in some of the lab, and then other in land use and solar. So there you can see there's some Y, there's some E, there's some ES. What are they? So in the bottom you will see what's the meaning means, and what are the meaning of those things. So Y means the forcing agent included. So Y means kind of yes, these are the radiative forcing agents in the global climate model. So if there is a Y, that means they are actually having radiative forcing impact on the climate. If there is Y, Earth system also on board. I don't know what I don't need to know about that. So E means concentration of forcing agent calculated interactively driven by. So these are the calculated things. ES is the calculated thing, something like that. And NA is that forcing is not included in the historical or future scenario simulation. So the some of those NA you see not applicable here. So they didn't have any they didn't have any impact of black carbon didn't have any impact in this. These are the model XS 1.0, XS 1.3. So these are all the models that used these things. Like for if you just go through this XS 1.0, XS 1.0 actually considered carbon dioxide, methane, nitrogen oxide, troposphere, all of them. They had uh, already data on that, and they calculated data for sulfur dioxide. E is calculated, as I already told you. They didn't include nitrate in their model. They didn't include land use in their model. So this is how you should interpret this model. So based on this model, there will be some question about. So let's start from the number one. In addition to ozone, what four other greenhouse gases or groups of greenhouse gases are included in nearly all the climate models? So all you need to do is to go here. In addition to the ozone, these two, or tropospheric, okay, ozone. Uh, Other than these two, what are other greenhouse gases? So there is carbon dioxide, methane, nitrogen dioxide, CFC. Which one? What four other greenhouse gases or groups of greenhouse gases are included in nearly all the climate models? So if you just avoid these two, uh, there are only four other options for you. So as you can see from the model, most of the models has Y, or at least if they don't have Y, they at least try to calculate them and include them in the model. So they are actually like there's I don't see there's only one NA for CFC, so it's not a big deal. But majority of them actually consider all four others. So that's number one question. There's another video about the concentration pathway. I've already described them in the presentation, so I don't need to talk about them again. I'm just going to go into the question directly. So, with respect to the representative concentration pathway, what is the largest of the four hypothesized relative forcings from pre-industrial times to 2100? So just follow the video. You'll be able to answer the question two. Then question three: what two emission scenarios most clearly represent the current trend in carbon dioxide emissions? So there is three uh, graph, three scenario. Number one that actually talks about carbon dioxide emissions. If you can see, this is actually talking about carbon dioxide emissions. Now then, this is actually talking about methane emissions. Then the next one is talking about nitrogen dioxide emissions. So the question actually asked about the carbon dioxide emissions. So what two other scenarios, what two emission scenarios most clearly represent the current trend? So this is the current trend in the black line. So you need to answer like which two scenarios are actually close to this trend. So as you can see, these and these are close to the current trend. So that's how you'll answer this question. Then below the projected carbon dioxide, methane, nitrogen dioxide concentration of the rest of the century. Why are carbon dioxide concentration increasing under the RCP 4.5 scenario when emissions are decreasing? So I've already talked to you about the uh, carbon dioxide lifetime. So even if you decrease the emission, carbon dioxide will still be there, the already emitted carbon dioxide. So that's how you need to answer it. Then the section 3 is actually talking about projected temperature change. I've already discussed these graph with you, how the temperature will change in the future. What's the question is asking, if you assume the current training temperature will continue to occur until 2035, how would you describe the projected change from the four different scenarios in near term? So 2016 to 2035. So all you need to do is to describe the trend in here, I guess. I believe the question is asking if using the current trend in temperature will continue to occur until. Yeah, I believe, yeah. You need to talk about these regions. So what's happening here? What's happening here? Sorry, I'm just using my finger. It's not right. You can see that. So my mouse pointer. So these are the thing. What's happening here? You need to talk about that in this question, and then these are the one that is talking about. Let me open that directly. There is description: projected temperature change in degrees Celsius, 1986 2015 to 2006 2035. So this is a comparison from these time zone 1986 to 2005, comparison of this time zone with this 2016 to 2035. So if you compare these from this scenario, this time frame to this time, you can see that the temperature actually is in the reddish, like deep red in the Arctic zone. What does that mean? That means the temperature change will be really evident in the Arctic region, but in the other region there will be some like increase of temperature. So most of them are actually yellow to red, so you don't see any blue, which actually means that a decrease in temperature. You don't see any blue, and you can confirm that with your own idea, like we never heard of temperature decreasing in the recent times, right? So definitely that also actually proves our point that temperature is actually, global warming is actually increasing. So based on that question, so you need to answer question 6 and 7. I believe you will know the answer. And then projected changes in evaporation and atmospheric moisture. So these are some of the scenarios. The climate model also project changes in SST, sea surface temperature, evaporation, and specific humidity. So one of them is about, this is about sea surface temperature, and this is about evaporation, and then this is about the specific humidity. So as you can see from the sea surface temperature, just pick a region. If you look at this region in the Arctic, you can see these are the only place where we can see that the sea surface temperature is actually in the upper side. So all other places have almost close to 1 or something like that, but this is the place, this is almost close to like probably 1.5. That means the increase of sea surface temperature. And then if you go to the evaporation, so for that same region that you've already talked, or that we have been talking about, for the same region, you can see that is the bluish. That means evaporation is here in the bluish, which means the evaporation will be highest in that region. In this region there is less evaporation. So and then again in the specific humidity, if evaporation increases, that means there will be the air will be more humid in this region. So you can see the Arctic will be more humid. uh, all are actually based on 4.5 RCP. So these are the things you need to know from here. Let me okay, then I'm not sure if my zoom in will work here. Okay, so what is the connection between a system and specific humidity? You can answer them here. And then, as you saw in the figure of the projected mean global temperature is a much larger temperature spread. So this is the four different scenarios. Just go through the description, answer this question. Like the idea is pretty much same. Like the temperature will increase and blah blah blah. So the multi-model average of surface air temperature. So how temperature will change, as you can see from RCP 8.5, temperature is really red. That means huge increase. So these are the some of the question. You will get the answer from this graph. Then there is the projected change in storms, precipitation, as well as soil moisture. If you look at these four scenarios, so this is like you see changes in tropical storm crack density from 2000 for 2081 to 2100 related to compared to 1986 to 2005. So compared to these last 20 years to compared to the final 20 years of this century, if you look at these, the number of models used. Okay, so we need to go to, so this is the south northern hemisphere. The northern hemisphere, this two, and this two is the southern hemisphere. Okay, so this is okay, yeah, yeah, yeah. So from this description you can see that this is the scenario for northern hemisphere when the RCP is 4.5. Northern hemisphere RCP 4.5, and for northern hemisphere if the RCP is 8.5, you can see there are more yellow section coming up here. What does that mean? That means the precipitation will be uh, this is the storm will be higher if RCP is increased, right? So the more yellow, the more there will be storm. As well as if you look at the southern hemisphere for RCP 4.5, there are some yellow region, and if you go for the RCP 8.5 scenario for the southern hemisphere, you can see there is some reddish dots. So that means it will be probably around 2.1, 2.7, something like that. That means the extratropical storm will increase even more in the southern hemisphere. So these are the idea of these graph. Answer the question 11, 12. Then Hadley circulation, you already studied the Hadley circulation here. So this is the ITCZ in the mid in the tropic. Then the circulation actually circulates this way in the north and this way in the south, and then at this point there are some precipitation happening here, and there's some precipitation happening in this region, the subtropical region. So you already studied those Hadley circulations. So there is another graph here. That is the projected changes in the annual average poleward age of the Hadley circulation. How the Hadley circulation is gonna change in the future. So if you just study these circulation, I'm just showing you. Okay. So if you look at here, so this is the 0 point. So like this intersection of these two, like you see this is zero here, this intersection of is zero here. So from historical data to RCP 2.4.5 for 2035, the mean northward displacement of Hadley cell will be in the upper side. What does that mean? That means that the RCP, Hadley cell will be moved northward, as like if you take the mean for about zero point 0.2, so northward. So that means these Hadley cell will move in the north, it will move even north. Then again, if you look at the southward direction, it was zero in the standard situation, it should be zero, but for 2035 it would be there. That means it went down, that means it moved southward. This, you see, this is the southward, this is the southward, so it moves southward. That means this Hadley cell will move in the north, it move even northern, in the south it will move even southern. So that's the idea of this. How is the white of the Hadley cell expected to change? So you can answer the question from these of my this description of mine. So again, these are the thing. I believe just you need to go through these graph and answer the question based on the analysis of your graph. I'm not going to go into the details. You already have the idea, I believe. I don't need to do that as well. You'll get to know them from the description. So projected changes to the cryosphere. So this is the cryosphere. Like this is the same thing that you studied probably in lab 9, I guess. Forgot the what lab you studied that, but this where you already studied it. So just go through the description again and see which one is actually really uh, which of the changes noted in the figure would you expect to continue throughout the rest of the century. So which one, like the from among the description, which one do you think will continue again and again in the future? So this is the sea ice in northern hemisphere reaches some extent. Okay, so there is a question, so let me go to the question directly. You'll definitely go to the description first. So under the RCP 4.5 scenario, what is the expected percentage change in sea ice extent in September from 1986 2005 to 2100? Okay, so what this graph is talking about, so this is the northern hemisphere sea ice extent. So this is the February situation and this is the September situation. So right now the sea ice is actually in this region. So for the scenario for R 8.5, for 6, for 4.5, for 2.6, the scenario will be that during February, in the at the second half of the 20th century, or probably in the whole after this century, the sea ice extent will be really low. If the situation of 8.5 continues, it will be in this region. If this is the orange is RCP6, the blue is 4.5. This is what happens when this is blue, like light blue, then 2.6 is actually defined as a dark blue. So this is the February scenario, this is the September scenario. So what is asking you to go for the RCP 4.5 scenario. So you need to go for the 4.5, that means the light blue. Then it's actually asking you to study from the September season. So then it's actually asking you to go for the percentage change in sea ice extent. How much percentage will be changed? How will we calculate them? So first of all you need to do is to see, find out the RCP 4.5. So this is 4.5, the light blue, and light blue is 4.5. So how will it change? So right now it's in here, that means around, let's say so that there is a comparison. So it's actually asking you from 1986 to compare that to this time with 2100. So what was the situation in 1986? You need to identify that first. So let's see. So 1986 to 2005, it was about in this region, and that was actually 7.1. So now it's in this 39, and in the 2000 2100 it would be around this region. So what you need to do actually is to, okay, all you need to do is to find, like, take this number here, number one, like 1986 to 2000. It was 1, and at the end of 2100 it was around -4. That means the change is -5. And then the present one is right now, this is the base number that you need to calculate, that is 39. So all you need to do is to divide. Let me see if I'm doing it right or not. Yeah, yeah. So I just calculated that. So All you need to do is to change, divide the change, that is 5, the change, by this base number 39, and then multiply it by 100, so you'll get the percentage. So that is question 19. And then go to this description. I believe don't need to explain them in details. Okay, so this is probably the last one I need to explain to you. So there is a question on question 22, which is projected to be larger contributor to sea level rise. So there is some scenario of sea level rising. There's some scenario. Uh, so and there is a question, which is the projected to be the larger contributor to sea level rise. So is it thermal expansion or is it the melting ice? So as you can see from this chart, that you have something about thermal expansion, but there's nothing about melting ice. But if you go to the description, you'll know that what melting ice. You see, sea level rise from melting ice sheets is the sum of Greenland SMB, Greenland DYN, and Antarctica. So if you need to count the melting ice situation, then you need to sum these three: SMB, DYN, and Antarctica. So SMB is zero point zero 0.01 to zero point zero 0.07, DYN is zero point zero 0.01 to zero point zero 0.06, and Antarctica is zero point zero 0.01 to zero point 0.10. So you need to sum all these three to get the melting ice value and compare it with the thermal expansion that's already there. So all you need to do is to, like, for your convenience, you can take don't take the average, just take the highest point. So if you, for RCP 2.6, let me show you how RCP 2.6 is done. Then you can do that for RCP 4.5, do that for RCP 8.5, and decide which one is greater impact. So if you take a thermal expansion, for RCP 2.6, thermal expansion has an impact of 0.18. But for RCP 2.6 melting ice, which actually is some of the SMB, DYN, and Antarctica, SMP has zero point zero 0.07, DYN is zero point zero 0.06, and Antarctica is zero point 0.10. So if you sum all these three, what will you get? You see, zero point zero 0.07 plus 0.06 for Greenland DYN plus 0.10. So it will be, the highest point will be 0.23 compared to thermal expansion, which is 0.18. So definitely for this scenario, the melting ice has greater impact, right? So greater impact to the sea level rise compared to thermal expansion. So do these for RCP 4.5, RCP 8.5. If all of those bolsters that melting ice is the main greater in contributor, then your answer should be melting ice. So see for yourself, answer the question about that. Then projected changes to biome, like, go through these. I believe you'll get to answer that easily. So again, there are some Google Earth files in here and there. So if you don't want to do that, just go through this section. This one, it's actually, you see, this is one of the Google Earth files that you can open, and this is another one. So the one Google Earth file is actually talking about the biome from 1976 to 2000, and another one is actually talking about biome from 2076 to 2100. So that is the previous century, the end of the previous century, and this is the end of this current century. So what's happening here, if you look at these two images side by side, you can see like how the biome is actually shifting. So if you just, let me take you from one point. So if you just look at this pinkish region, you see it was there now, and after 100 years, it's even in the close to the Arctic, right? So that means it was from these, it actually went up. So went up means it's actually moved northward. So that's what I told you in my presentation, that climate types are expected to shift northwards, right? And then also spatially decreasing the tundra. So as you can see, everything is moving northward, which actually is impacting these regions. So this is the blue, I don't know the color, what's the color name. For now, let's see, I don't know what the color is. Probably whitish blue. I know, I don't know. So whitish blue is ET. You see, if you look at this classification, that is ET. ET means tundra. You can confirm that from your previous lab 9, I guess. ET means tundra, and if you look at these in here, you see there's not much ET left after 100 years, right? So the amount of ET was there in 1976 to 2000, that is now is decreasing. So tundra is the one that is actually decreasing. That is one of your question, and also tundra is a climate type, and tundra is also a biome. You already know that tundra is the one that is at the same time climate type as well as biome. So that's the one you need to answer. And then final one, what processes resulting from the melting of tundra would lead to increased global warming? So go through this depiction, and lots of things they've been discussed, they're discussing here, but you don't need to go through all of this because the question is asking you melting of tundra, what's happening in these uh, terminology. So go here and see, look out for tundra. So yeah, here's a tundra. So what's happening here, you can go for the description. So if the melting of tundra is happening, lakes drain, form as permafrost, permafrost is turning warmer regions. So there's if the tundra is actually melting, so lots of new lands are actually exposing, and that new lands are actually emitting methane. So that's what happening in tundra. And as you know, methane is a greenhouse gases. So let me go to the first one that I opened. Yeah, here. So you see, methane is a greenhouse gas here in this chart. So methane has radiative forcing impact, right? So definitely, if that has radiative forcing, that means that actually helps like negatively to increase the global warming. So that's one of the question. And then the three research questions, you need to write a brief summary of what you learned in this lab, in this for these three research questions. So that's all from now for now. And this is the final time, this is the final lab for this weather and climate. I believe you've enjoyed this lab. This is personally, I take another lab that is landforms, introduction to landforms, and this weather and climate. Among these two, I really like weather and climate because it's really practical. Like you can confirm this idea, the idea of this lab, with your own understanding, the or whatever you have been hearing on the news so far. So from the scientists. So this is really striking. For some of those things were really striking for me as well. So, and this lab is really interesting to study the simulation, the animation, the video, and everything was really structured. And I personally like this lab. And I didn't get a chance to meet you personally, but uh, I wish you all the best for your future endeavor. And let me know if you have any question, any confusion regarding the lab, or regarding the grading, or whatever it is. Just shoot me an email with all of your concerns. So probably next week, next Friday will be the last office hour for from me for this lab. So if any of you want to meet me during my office hour, you can connect me on this Friday. All the best for this lab particularly, and all the best for you. Have a good day.